So it's fair to say that the approach used in the first portion was pretty wishy-washy. At the base, it was based off of how stale you and your team felt that a beer gets over time, and that's clearly very subjective. While it provided a lot of control and a lot of freedom to align the brewery goals with the brewery practices, it was not robust. What would be more useful is something altogether better grounded in the science of beer. Fortunately, the framework we used leaves us lots of room to fiddle in our elements of beer science bit by bit using the same basic structure. The math in this episode looks more complicated the way it's written, but I promise it's not actually any more complicated.
Recalling from previously, our age score looked more or less like this. We have an age in days divided by a maximum age in days. We have our storage conditions, our temperature aging factor. We have product characteristics, our beer style aging factor, and I've decided to throw the package factor back in there. All of those together combine to make our age score. Other aspects of storage that we control, like light exposure or humidity or oxygen levels, could be incorporated here as well. However, the beer style aging factor is really the elephant in the room to address. Instead of generating the beer style aging factor by ranking beers through a sensory panel approach, what if we instead tried to calculate one? The taste test from our first try at the age score is an accumulation of a variety of beer characteristics interacting together in complicated biochemistry as perceived by the panelists themselves. If we look at these beer characteristics individually, perhaps we can combine them usefully. By applying software in our collective knowledge of science and beer, we can bring the scores we developed earlier that much closer to reality using available measurements. Rather than using our taste test data and our more gut feelings on how stale a beer tastes, we can use reference styles to establish numerical relations. A percentage alcohol versus a benchmark percentage alcohol, an IBU concentration versus a benchmark IBU concentration, and so on with other beer factors. We can also establish a reference beer in terms of package type. We'll choose draft beer as our reference point because that tends to be a little bit more consistent quality than cans in most craft breweries. So here's one way we could attempt to establish a beer style aging factor numeric. It adds and weights several aspects of a given beer recipe that are likely to affect overall shelf stability, notably our alcohol concentration, our IBU concentration, and our overall carbonation, which is another way of indirectly measuring our pH and our total package pressure. The scalars you see in the equation are used to weight the relative impacts of the different staling factors and to make the baseline beer style aging factor 1.0.
If you're sitting there saying, his weightings are all bullshit and what he measures is dumb, this is where you can take things and mold them to your own specifications. Down here is what we call the general form of the equation. Here you can plug in any aspect of beer that you think has a significant impact on shelf life. If you want to improve your shelf life by including, say, initial concentrations of 4-vinyl glycol or cohumulone or whatever, this is where you do it and how.
Going from our general form back to something we can more usefully use, we have to calculate our ABV and IBU factors to start reconstituting our beer style aging factor. These are the simple formulas that are easy to set up in a spreadsheet to calculate an ABV and IBU factor. Specifically, the higher the ABV of any given beer relative to its reference beer, and similarly for the IBU, the lower the ABV or IBU factor, and the lower the resultant beer style aging factor will be, and thus the slower the beer will seem to age. If the products your brewery has on offer includes a lot of beers that are at the extreme ends of the IBU or alcohol ranges, you may wish to consider this alternative but more computationally intensive way to calculate ABV and IBU factors. This style of calculation makes more normalized results across a wider range. The end result of the simple and the alternative factors doesn't show much practical difference unless the brewery is using those products at the extremes of the range. If we were applying our calculations to a very large database, it might justify the use of the simpler form of the ABV factor simply for the sake of computational efficiency. An additional comment that I've made here reflects one of the peculiarities of brewing. If you have a high alcohol, high IBU barley wine, for example, and your reference product is below 5%, you could end up with an ABV factor, or even a beer style aging factor, that is below 1. However, A high IBU, high alcohol barley wine is going to have a long shelf life anyways. In fact, drinking it too soon is more likely a mistake, so it's maybe not that much to worry about. And we carry on calculating the carbonation factor in very much the same fashion. Once again, we're choosing something that will limit the impacts of aging the higher it gets, which is why it is on the denominator. If we were to include another beer aspect that was the contrary, like say total package oxygen, then we would put it in the numerator. The carbonation level of a packaged product can be considered to affect its overall shelf stability for a few reasons. Number one, the higher package pressure inhibits increased microbial activity from simple osmotic pressure. As well, a more highly carbonated substance has a lower pH, and this will also limit the impacts of any type of fouling or yeast reactivation. Realistically as well, a customer expects a product to be carbonated. The higher the initial carbonation, the more it can lose on the shelf and still be considered broadly viable by the consumer, whether or not this is an ideal circumstance.
Here again we have the general form representation to give you all the power you need to bend this mathematical tool to your will. Use it wisely, my friends. Here you can take any aspect that you think affects the shelf life of your beer and normalize it to a reference point to put it to work for you.
So looking back at the formula that I proposed for the beer style aging factor, let's remember that I chose this arbitrarily. Indeed, I partly chose the scalars to be non-whole numbers, deliberately to emphasize the fact that they do not have to be integers. The weighting factors here can also be more simply put to say that the alcohol factor is the most important, the IBU factor is the second most important, and the carbonation factor is the least important. I've assigned them values in descending order, 2, 1.5, and 1. When these weighting factors are assigned, though, it does start to imply a relative importance to them. It implies that IBU is 1.5 times as important to shelf stability as carbonation, or that alcohol is twice as important as carbonation, and those are insane simplifications. But a simplification is all we're ever going to really get out of this, and we can fine-tune these later. And so we start to see with the weightings being applied that our data-driven approach, while it may sound more attractive, it also has some uncertainty buried in the math. There's a lot of subjectivity to those weightings, and just like with the last time, there's a lot of fine-tuning that can go on. This new method also relies on the beers being produced as writ, not behaving as observed. We all know that in a small brewery, just because the recipe says the beer has 5.5%, doesn't mean that the can you get at the retail store actually has 5.5% alcohol in it time after time after time. Testing things on a more empirical basis gets more real-world results, whereas this relies more on our theory and our practices being as perfect as possible. Back when I was a young engineering student, I got coached in a few of the old-school methods for controlling beer aging with respect to temperature. Now, this was mostly introduced in the context of a pasteurizer and how long is too long, and how things related to inline pasteurization for kegs as it compared to tunnel pasteurization for bottles. However, it basically goes that beer at pasteurization temperature for an hour tastes the same as beer that was in a hot room in the summer for a day, beer that's been at room temperature for 3 weeks, beer that's been at cellar temperature for 3 months, or beer that's been at a fridge temperature for a year. If we limit ourselves to the data points that are closer to our actual storage temperatures, we get a curve fit that looks a little like this. It's some gross numbers. For our purposes, we still use a maximum reference age of a year, and from that, we get our temperature scaling factor. And this is the graph of that same data and the curve fit as well. You'll see I've identified here a, quote, line of constant relative staleness. That's just my way to graph the heuristic that I was taught. Beer tastes as old in one condition as another. They're both the same relative staleness. So it is a line of constant relative staleness based on storage temperature. And this same chart was used to get the simple temperature aging factors from our first session. What I did was I just took crudely rounded values from this curve to say that one was twice as much as another, which was twice as much as the next. A very, very rudimentary curve fit.
Now, in our first go at the beer style aging factor, we totally skipped the package factor. This is because the first brewery we were looking at, there wasn't much point in comparing cans and kegs because the markets were basically mutually exclusive. But as we're trying to push things in a more data-driven direction, it's appropriate to bring it back in. Especially in a craft setting, the type of package a beer goes in is a huge impact on its overall shelf stability. Now, it's pretty much impossible to know how much older a can of any given beer will taste compared to a keg of the identical beer that's being handled in the identical fashion, but we're going to be rude, crude, and quick to get some approximations. Our reference beer type will be kegged and have a package factor of 1. We will assign cans a package factor of 2. This implies that canned beer tastes twice as old as kegged beer, which could be an overestimate, an underestimate. In fact, the only thing we know is that it's probably not exactly 2, but we know also for absolute certain that unless someone has made some catastrophic errors, the kegged beer from a craft brewery will taste fresher than the canned beer over a given time frame. And since we know that it's going to taste fresher than the can, all we really need to do is push our numbers in the direction that reflects that.
When it comes to color, I probably spent more time debating whether or not to include color in this than I did pH. It's partly because color is easy to check, and it's easy to get a feel for color from a recipe. Color also conveniently allies itself with pH, making it a very attractive thing to include. However, when I considered the realities of how highly colored beers perform as they age on the shelf, I felt this was probably going to bring more noise into the situation than clarity. I think the complication that highly colored beers brings to this underscores the benefits of the earlier method that used our taste buds to guide our judgment. Here, guided by numbers, there's nothing to appreciate how highly colored beers can enjoy a certain amount of maturity over time. We've now made all the constituent parts to start going back to our data-driven age score and our must-sell score. We have our beer style aging factor, we know how to calculate our carbonation factors, our ABV factors, our IBU factors, we have established our temperature staling factor, and we still have our formulas for age score and must-sell score from before. Armed with our formulas, we return to the dataset we had from earlier. These are the tabulated data-driven age scores from the exact same beers we compared in the first session. We'll begin with some reality checks. The fresh amber that was packaged that same day has a score of 0 again, as it should. The Radler, stored on the brewery floor, has a high score, again, as very much it should. But of note, this model puts the IPA stored in the basement at a much higher risk of being stale than the simple model had, and this is largely because of the package factor that we have included. Is this perhaps too high? The pattern of the scores remains broadly the same as it had previously, which is good news. It means we haven't strayed too far from the course yet. Turning to a graph to visualize our information, we see the simple age score and the data-driven age score compared on this chart. Here we can see emphasized the differences between the two, notably that IPA that is now shot up to the top of our stale pile, mostly because it's in cans. We'll turn around and do the same thing with the must-sell score that we did with the age score. Again, beginning with our reality check, the beer that was just packaged is still at 0. It doesn't have any sales pressure on it at all. We also see the Radler that is stored on the floor has a medium-high must-sell score. It's good that it's not low, but it is perhaps slightly concerning. Also of note, we have those IPAs that we have a significant quantity of in stock bubbling way up into our must-sell scores, because they're both getting old and they're high in stock. Returning to our graphical method, we put the data-driven must-sell scores here against the simple must-sell scores we got in the first session. And you'll notice the major difference we see is this IPA that was in cans in the basement that there is a significant stock of has gone all the way to the top of our must-sell score in a big way. This big difference is primarily due to the combination of the package factor and other tiny changes we've made, pushing this must-sell score way through the roof. In other words, someone should sell that IPA pronto. So if you've joined me this far down this rabbit hole, you've probably come to agree with me that dimensionless numbers can be usefully applied in the brewery, and further that the age score and must-sell score can be usefully applied more specifically. We've discussed a lot of their limitations along the way, and we know that a lot of these are inaccurate and rough measures, but they can still be useful. In terms of the limitations of dimensionless numbers in the brewery, we've also seen that if you don't know how something works or aren't sure how it's going to interact, using a dimensionless number to study it is probably not a good idea. We also know that crap in makes for crap out. If we don't have good data coming in, we won't get good judgments coming out.
We'll look at other dimensionless numbers we could apply in the brewery in the final episode of this section, but let's discuss where else we could take this idea we have right here. Firstly, the arbitrary weights I assigned to the beer style aging factors could be refined through intensive and exhaustive literature review. Secondly, there are breweries out there with large databases of cached information on old batches sitting, waiting to be analyzed. Especially product recall and customer complaint records from the largest breweries collated with their storage records. That could produce some very interesting results. Sometimes we can solve new problems by trying to unravel past mysteries, and big databases are a treasure trove of information. I hope you enjoyed that, and I hope you'll come back for episode 3, where we take a final look at dimensionless numbers in the brewery and take a look at some other examples I've come up with that might be able to help you out.